It's my real pleasure to introduce Dr. Sangyoun Gee. He's currently a principal laser scientist at Elixir in Fremont, California. He is also currently a adjunct lecturer here at Sonoma State University, where he teaches our electricity and magnetism class for majors this semester, and next semester he'll be teaching our optics class. He came to the area of Northern California here in Petaluma because of Radiance, which was a Petaluma-based precision manufacturing solution company using femtosecond laser technology. And as I said, he's taken this real-world experience to his new company, Elixir, that he works at. He received his bachelor's and master's of science in physics from Yonsei University in Seoul, Korea. His PhD is in physics from the University of Central Florida. He spent time as a research scientist at the Central Florida after his degree. He also went and was an assistant professor at Gwangju Institute of Science and Technology in Korea before moving here. And as I said, joining Radiance in 2012, which brought him to our area. Well, we're thrilled to have him in the area and to have his expertise as he talks about very fast lasers. Let's welcome Dr. Sangyoun Gee.
Thank you for the introduction. It's my pleasure to have a chance to talk about science and application of ultra-short pulse lasers. I really enjoyed this topic, and I hope you enjoy this too. Here's the outline of today's talk. First, I will briefly discuss about the basics of the ultra-short pulse lasers, about the why we care about short pulses, and then how do we generate the short pulses, and then how we measure them. And then after that, I will talk about the couple of examples of applications, which is the optical comb generation and optical clock. And then since the laser can generate pulses, we can use the pulse as a tick signal, and then it works as a clock. And for that, we need a very low noise laser. And so how to make the low noise laser. And then optics has a huge bandwidth. Because of that, it can be used to overcome some of the limitation in electronics. And so I'll talk about the optical signal processing. As an example, I will talk a little bit about the photonics analog digital converter. And then I will also talk about the application of the short pulse laser in the nonlinear optics. And then finally, I'll talk about the precision laser machining using the high power lasers. So first of all, when we say the short pulse, how short is short? The shortest pulse ever created so far is just 67 attosecond. 1 attosecond is the 1/1,000,000 of a millionth second. So it's really short. To just give you an idea, if you compare with the age of the universe, people say that age of universe is about 14 billion years. And then it's about 4.4 10 to 17 seconds. So if you take 1 second out of the age of the universe, which is almost the same as the shortest pulse width out of 1 second. Wow. It's really short. And in fact, this is the shortest or fastest event that mankind has ever created. So before we go on, I need to point out a few things about the short pulse. When we talk about the short pulse, it's the characteristic in time domain. Pulse is really short. But we also have to look at the spectral behavior or spectral characteristic. The spectral domain picture of the pulse and the temporal domain pictures are like head and tails of a coin. They always comes together. And then they are connected by the Fourier transform. So let's say we have a long pulse, then I can picture something like that. And then if you look at the spectrum, it has a very, very narrow line width. If you go to the short pulse, then in time domain, the pulse is very short. And then at the same time, since the pulse has been compressed in time domain, it has a very high intensity. when you look at it in the spectral domain, it has a very broad bandwidth. So between the pulse width and then bandwidth, there is a very simple relationship. They are inversely proportional to each other. When we do the short pulse laser application, mostly we are taking advantage of these three facts. One is either using this very short nature of the pulse, or very intense energy nature, or the very broad bandwidth. Those three are the main idea of using the short pulse lasers. And if we have not only just one pulse, but the train of pulses, then we can imagine something like this. All the pulses are equally spaced in time. And then if you look at the spectrum of this pulse, then something similar happens in spectral domain. The spectrum has been segmented in small pieces, and they are also equally spaced. And between the pulse interval, the tau REP, and then between the separate spacing between this spectral component, REF, there is a simple relationship. Again, they are inversely proportional to each other. And then these segment, we call it mode. I will revisit the mode again. So having that in mind, let's just talk about why we care about the short pulse lasers. There are so many applications. First of all, if you want to study very fast dynamic, then sometimes you need a probe signal, and the probe signal has to be shorter than the dynamic itself. Since the pulse is the shortest thing, then that makes the very good candidate to probe this very fast dynamics. When we do the phone call, the signal goes to the cell tower, and then after the cell tower, it goes to the next cell tower through the optical fiber. And what's transmitting through the optical fiber is the pulses of light. So we need the optical pulse for the communication. It can be used in the signal processing. It is used in the spectroscopy. And then it can be used to make a clock. And it can be used in many nonlinear optics, research and application. It can be used to generate the terahertz radiation. It can be used in medical imaging. It can be used in the precision machining. And then people can use the intense pulse to accelerate electrons. And then once the electron is accelerated, we can use it to generate X-ray. And then also, of course, we can use it for the nuclear fusion. And these are just a few. Actually, there are a lot more applications. So since the short pulse laser has this many of the applications, that's why we care. So let's first think about how we can generate such a short pulse. Bottom line is the mode locking technique, or mode lock laser. So when you say mode lock, what is mode, and then what is locking? So let's go over it one by one. First, we have to start with the laser cavity. In order to make the laser cavity, we need two mirrors, one mirror and another mirror. If their mirrors are parallel to each other, we can trap the light in between these two mirrors. So light will just go back and forth and permanently and is trapped in there. That's the laser cavity. But not all kind of radiation can be trapped inside the cavity. It has to satisfy certain condition. Simply speaking, it's called the standing wave condition, which means the wavelength should be integer multiple of twice of the cavity length. Then it will be allowed to stay inside the laser cavity. And then this m can be any positive integer. In fact, for the given laser cavity, there are more than one mode allowed. Actually, there are infinitely many modes, as this picture shows. And then I just numbered it by m, 1, 2, 3, 4. And then as the m value or mode number increase, the number of node in this amplitude increase. In reality, the most commonly used lasers, this m value is somewhere around 10 million or a little higher. But ballpark is about 10 million. And when we make it into a laser, then usually about hundreds of thousand modes excited at the same time. And then this is the standing wave condition, and it's expressed in terms of wavelengths. And we can also express in terms of the frequency. Then we can write this way. And as you can see, the frequency will be equally spaced. And then as the m increases, it will just proportional to the integer multiple by this number, c over 2l. So there will be infinitely many numbers. And then please keep that in mind. I will revisit this again. And so let's consider superposing different mode. Here I just drew a couple of modes, mode number 1 and 2 and 3 and 4, and there are many. And since this amplitude of the mode is electric field, and then they are actually vectors, so they can be added as a vector. If I superpose the mode 1 and 2, then we'll get something like this. This is very easy to see. For the mode 1, it's all amplitude is positive, and then mode 2, left-hand side is positive and right-hand side is negative. So if you add them together, on the left-hand side, it will be constructively added, right-hand side will be destructively added. So we see the increase of the amplitude in left-hand side. If I add mode 1 and 2 and 3, then it will be something like this. And then 1 and 2 and 3 and 4, then we'll get this. And then you may have noticed there is a pattern. As we add more and more modes, it becomes more localized. Amplitude becomes more localized. So if we add a lot of modes together, then we'll actually get pulse. And that's how we generate pulses from mode locking. But there's a catch. Again, these are 4 modes that I shown in the previous slide. For the mode number 3, I flip the sign of the amplitude. Or I change the phase of this mode by 180 degrees. So the positive amplitude become negative and negative become positive. And then if we do the superposition with this condition, let's see what happens. Mode 1 and 2 is the same as the previous case. But if I add 1 and 2 and 3, this is what we get. If I add 1 and 3 and 4, then this is what we get. If I add many, I get something like this. So that tells you, it's not just adding many modes. Actually, to generate the short pulse, the phase of the mode has to be fixed. And then also, if the phase of each mode is all equal, then that's better. Yes?
Is that superposition at the bottom what you would get if only the third mode is out of phase?
No, this is the superposition of the many of them.
So more than just that one node are out of phase.
In this case, yeah, I mean, this is not really very accurate. It is very accurate up to this one, but this one I just scribbled it. It was difficult to draw. But anyway, when you add all together, you don't really get the nice pulse as you've seen in the previous slide. So in order to make a short pulse, the phase of each mode has to be fixed or locked. That's where the term mode locking is coming from. You have to have a many mode, and the phase of the mode has to be locked. And then once that is done, then you get short pulses. Then the next question is, there are like 100,000 modes, and how are you going to lock the phase of each one? And then there are many tricks to achieve it. And this is a whole field, and people do that for a living, like myself. But I will just give you a few simple examples. This is the simple, one of the mode locking technique called active mode locking. Let's assume we have a laser cavity. And let's assume there's a guy with a clock, and then there's a door. So this guy open and close the door at a given time. And then let's assume for somehow there was a surge of radiation or light coming in. Usually it's created from the noise. And when it comes, and then if this guy happened to open the door, then this pulse will just go through. And then you will hit the mirror and come back. And then again, if this guy happened to open the door at the same time, then this pulse will go through it. And then if this guy is really synchronized with this pulse, then this pulse will survive and then travel, go back and forth. Other pulses, if it's not synchronized with this guy, then it will just diminish. And then this is the one way to generate pulse. Here's the device, actual device, that does the role of this door. This is electro-optic modulator. It's a fiberized, so we have a one input fiber and output fiber. Light goes through this fiber and then comes out of this fiber. And then we have an electric port, and then by this electric port, we apply the electrical signal to open and close the door. This is one simple view of the mode locking technique. Another mode locking technique is called the passive mode locking. Instead of a door with a guy, we can imagine all time this ferry boat. The ferry boat does not operate by a fixed schedule. It just sits in the harbor, and then whenever there's enough passenger gathered, then this boat will depart. So the similar thing happened. Out of the noise, let's say there is some pulse came in, and then if the pulse is weak, then this pulse cannot really go through it. The device that does this role is called the satchel observer, and then this device absorbs all the light. But once the intensity of this noise pulse is over the threshold, then this bleach the satchel observer, and then this guy becomes transparent or very low in loss. So the strong pulse can go through it, like when there's enough passenger in the ferry boat and the boat can travel. So this pulse, if that is strong enough and goes through it and then comes back, and then when it returns, the same thing happens. If that is strong enough, it can bleach the satchel observer and then continue the trip. Any weak pulses will be all absorbed by this guy. And the actual device that does this role, there are many different types, but this is one example. We call the satchel observer mirror. This is made out of semiconductor. And then instead of having a window, we use it as a mirror. And then this guy has a high absorption, but for the intense light coming in, this becomes a very high reflectivity, and they reflect the light. It works as a low loss device. So that is the called the passive mode locking thing and mode locking method. And then I just explain in a very simple manner. So let's assume that we have a pulse, and then we have to measure it now. And the electronics, the fastest signal that electronics can handle is in the order of tens of picosecond. But we are talking about the pulses at the femtosecond and attosecond. So electronics can't really see the difference in the short pulse. We need some special way to do it. And there are, again, many techniques that has been developed, such as autocorrelation, cross-correlation, frog, spider, and street camera, and so on and so on. I'll just give you one method, the autocorrelation, to have an idea. So let's see, we have a short pulse, it comes coming in, and then we split the pulse using the beam splitter. When we split the pulse using the beam splitter, it only split the energy. All the spectral and temporal characteristic of the pulse is preserved after the splitter. And then they travel through different path lengths, and then using this another similar beam splitter, we can actually combine these two pulses back. But when we combine those two pulses, we arrange in such a way that the path length of the one pulse is a little bit larger than the other. So these two pulses are separated in time by this delay, delta tau. When we have these two pulses, we send these two pulses into the nonlinear crystal. And what this nonlinear crystal does is that the nonlinear crystal creates a signal that is proportional to the overlap of those two pulses. If these two pulses do not overlap, then there will be no signal. And the more they overlap, the stronger the signal, as you can see here. When we have two pulses, they are barely overlapped, then only the portion that overlap this crystal generates signal. If the two pulses are completely overlapped, then we have a strongest signal. And then we change the delay between those two pulses while we're measuring the signal. Then we can plot something like this. this horizontal axis is the delay between those two pulses, and then this is the signal from the nonlinear crystal. And then this plot we call the autocorrelation signal. There is a very simple relationship between width of this autocorrelation signal and then actual pulse width. And they're actually proportional to each other. So from this measurement, we can actually estimate the pulse width. So now I have given you the basics of the short pulse laser. Let me switch gear and then talk about the applications of the short pulse laser. First example is the optical cone. I just explained that using the autocorrelation method, we can measure the pulse width. It works well when the pulse is short, but still not so short. But as the pulse gets shorter and shorter, then at one point, there are only a couple of optical cycles inside the pulse. Then using this autocorrelation becomes a little bit tricky. So let's consider this case. We have two pulses, A and B, and then if you look at the envelope of these two pulses, they are identical. So if you're talking about the pulse width, these two has the same pulse width. But now we have maybe about 3 cycles in this envelope. And then if you do the autocorrelation of this, and then if you do this autocorrelation, they will have a very different result because there is a phase difference. As you can see here, this pulse looks more like a sine wave within this envelope, and then this one looks more like this one looks like a cosine, this one looks more like a sine. And then if you do the autocorrelation of this and then autocorrelation of this, they will have a different value. So, I mean, this kind of problem we never worried about when the pulse was long enough, but as the pulse gets shorter, now we have to worry about this kind of case. This was the late 1990s. And when these researchers reported this effect, they not only sending us a warning, they did some more work. They actually found out when that happened, there is a slow drift of the phase from one pulse to the neighboring pulse, as it was shown here, delta phi. And then this value accumulate as you go on to the next and next pulses. And this is a temporal domain view. If you look at this pulse in the spectral domain, we see many modes in it. But remember earlier when I introduced what the mode locking is, I said the frequency of each mode should be given this way. So this is integer multiple of this mode spacing. But in reality, when we look closely, we found out there's an offset frequency, F0. And then they found that this F0 is closely related to this small phase drift. The time derivative of this phase drift is the same as this offset frequency. We call this offset frequency as a CEO, the carrier envelope offset frequency. Let me tell you why that is so important. If you look at each mode, then when the frequency of the mode is given this way, we can control the repetition frequency, which is the separation between mode, which is in the range of tens of megahertz. We can control the precision of 1 hertz, or even better than that. So the mode spacing is very precise. But when you look at this offset frequency, again, this is the same order of magnitude, about tens of megahertz, but the precision is really poor. So if my finger, these are the mode, and then if you look at the spectrum of this, their spacing is really, really precise. We can control it with a high precision, but they kind of moves like this. And then as it moves around, it's really hard to catch individual mode. But there was a really, really, in the optics community, people has been dreaming about all the mode are really fixed. So they've been dreaming about having something like optical version of function generator or signal generator. In any even elementary lab, people have a function generator. You have a box and then there's a dial, and then if you set the dial at 500, then they will give you a 500 hertz signal, and then you can change the amplitude and phase. People has been dreaming about having something like that in optical domain, but which is very hard to get because of that problem. And then also the optical frequency is in the 10 to 14 hertz range, so the frequency is really high. Few years later, in 2000, the researchers at Bell Lab reported something very unusual. This seems like a completely unrelated to the work that I've been just mentioned. He's been playing with the novel type of optical fiber. It's called the photonic crystal fiber. It looks like this. And then if you send the light into the center of it, then you will be guided and then you will propagate through the fiber. What's unique about this fiber is that this fiber has a very, very high nonlinearity. So if you send a pulse into the one end of the fiber, what comes out of the other end of the fiber will have a tremendously broad optical spectrum. This is the result. This dotted line is the spectrum of the input pulse, and then this solid line is the output. It just blew out the mind. When people saw this was really shocking. And then few years later, some clever people combined those two. First, they brought the pulse from the short pulse laser and then send it into those fiber and then broaden the spectrum. So the spectrum becomes so broad, it's more than several octaves. And then they pick one mode out of this broad optical spectrum. So in this picture, this solid line is the original spectrum from the laser, and then this dotted line is the broadened spectrum after this nonlinear fiber. And then they pick the one mode, let's say F mode, and then the frequency will be given like this: F CEO plus n times of repetition rate. And then they send this mode into the nonlinear second harmonic crystal. Second harmonic crystal double the frequency. Actually, in fact, in my this pointer, inside my pointer, there is a second harmonic crystal. There is a laser diode. It generates a 1 micrometer wavelength light, and then it goes to the second harmonic crystal. It doubles the frequency, becomes 500 nanometer, and then now it becomes visible. So the similar crystal was used to double the frequency of this light, and then we'll get this frequency. And then, since the spectrum has been broadened so much, we pick the mode then is 1 octave higher than this. So this is a F2N. If you look at this frequency, this is a CEO plus CEO frequency plus 2 times of n multiplied by the repetition rate. So if you compare this frequency and this frequency, they're very similar, but difference is the FCO frequency. Detection of this FCO frequency is very easy. If you send those two modes into the photodetector and then look at the beat signal, you can easily detect it. This CEO frequency is actually a function of the cavity length or intracavity dispersion or pump level, many parameters. Controlling the CEO is not difficult at all. It was really detecting it. That was really difficult thing. But using this technique, they were able to measure the offset frequency very precisely. Once this is measured, then they create the feedback loop to make this guy 0 by controlling the pump power or cavity length. And then when that is done, this FCO frequency will be 0, so laser frequency will be exactly integer multiple of this repetition rate with the precision of hertz. That is really, really remarkable work. And as a result, in 2005, John Holtz and then Teddy Hench got the Nobel Prize for this work. So that is the optical comb work. And then let me talk about the next application, low noise mode lock generation. Before we talk about noise of mode, we have to first define what the noise of mode lock laser is. Let's first imagine very ideal case. We have a train of pulses, and then each pulses are identical to each other, completely identical. So it's just the replica of them. Then in this case, we call this ideal pulse train. And then anything deviate from this is considered as a noise. For example, there can be an irregularity of the pulse position. The pulse comes a little bit earlier or comes a little bit later. Then those kind of irregularity, we call it timing zero noise. Amplitude can fluctuate. Some may be a little bit stronger, some may be a little bit short. This we call it amplitude noise. Pulse width may fluctuate a little bit when you look at the pulse train. That is a pulse width noise. If you look at the individual pulse, there could be a little bit of difference in the optical frequency. Then it's called as a frequency noise. And then there could be a little bit of the fluctuation in the phase, and then that is optical phase noise. There are many different noises. When you look at the optical spectrum, there are many modes, and then each mode can fluctuate. If that happens, we call it mode partition noise. When you look at the certain cases, the pulse groups together, and then there could be a fluctuation between different pulse groups. And then if that happens, we call it supermode noise. I will have a chance to talk about it later. So anything that deviates from the ideal case are considered as noise. And the origins of noise are also many. But roughly we can divide in two groups. One is the classical noise, the other one is a quantum mechanical noise. In this simple laser model, the pump light, the pump energy will go into the gain. And the pump energy may have some sort of fluctuation. That is a classical type of noise. And then when the pump energy get into the gain, there is ambiguity. Some energy will go into the gain, some energy will not. This is a quantum mechanical process. So there is a quantum noise involved. Once the energy goes to the gain medium, some will go to the cavity, but some will not. And then again, there is a quantum mechanical noise. Here's a laser cavity. Laser cavity may, for example, cavity length can fluctuate depending on the environment. If there is somebody walks by and then footstep vibration will go into the laser cavity, that we consider the classical noise. When the energy gets into the cavity and then it goes out through the out coupler, that process is a quantum mechanical process. So there are many different sources, and then we have to consider all that to model properly. And there are, again, many different models, and the model is quite complicated. But I will just show you one thing. When everything is done, then we expect to have this kind of plot. Vertical axis is the frequency of the noise, and the horizontal axis, and vertical axis is the amplitude or strength of each noise spectral component. And we call it, this is the noise spectral density. And the typical behavior is that it has a plateau at low frequency, and then there's a knee, and then after the knee, noise dropped, usually proportional to the 1/f squared. That's the typical behavior. And the different model predict a little bit different behavior, but if you look at the noise spectral density, they're almost the same. There's a plateau and the knee, and then it drops, and they're proportional to this 1/f squared. So if you want to reduce the noise in the laser, mode lock laser, this actual model is very complicated, but the basic idea is very simple. It can be found from this quality factor. Quality factor, the concept of quality factor is used, it's very broad. It's used in the mechanical oscillator, electrical oscillator, laser oscillator, acoustic oscillator. It can be used in any kind of oscillator. It is defined by the energy stored inside the oscillator or resonator divided by the energy released in each cycle. And then that is intimately related to the line width of the output. To understand this, let me make an analogy with this hydraulic dam. Let's see, these are the hydraulic dam, and this is water reservoir, and then there's an inflow of the water and then outflow of water. The inflow of water can be like any precipitation or melted glacier water or whatever that is. If the reservoir is big, then even if there is a drought or flood, you will maintain almost the same water level. So the outflow of water will be very regular. It will not really fluctuate that much. If the reservoir size is small, then if there's any external disturbance, if there's dry season, that will just dry up the reservoir, and then the outflow will be diminished. So in this case, the outflow will be very irregular, while in this case, the outflow will be very regular. This case corresponds to the high quality factor case. This is a low quality factor case. And then when we have a very high quality factor reservoir oscillator, the outflow is regular, and the regular means noise is very low. And that's the idea. When we make the laser cavity, we want to make the quality factor of laser very high. Then the laser will suffer less noise. And how do we make the quality factor high? One way is putting more photon inside the laser cavity, but it has a limitation. As the intensity gets larger and larger, there's a nonlinearity. The other method is the physically making the laser cavity really, really large. But then laser cavity is made out of two mirrors, and then you have to separate the two mirrors far away, and then practically it's very hard to maintain them stable. One trick to do that is using optical fiber. If you make the laser cavity using optical fiber, then you can make the laser cavity very large. You just bring a spool of fiber, and then you can make the laser cavity which is 100 meters long. So when you do that, you get this kind of result. This is the noise spectral density of this normal laser, the short laser cavity. And then once you make the laser cavity really long using fiber, you get this. As you can see, the knee frequency has been lowered. So the noise, at the high frequency, noise has been almost diminished. So it really helps by having the large cavity or making the high quality factor laser. But then problem is that when you have a very, very long cavity, the pulse that comes out has a very, very low frequency because the pulse comes out every one round trip. So in this case, pulse comes out maybe every 10 megahertz, but in this case, it comes out maybe every 100 hertz, so very low rate. And practically, it's not really useful. We need a pulse that comes out in the order of megahertz range. So there's a trick to achieve that. If you put more than one pulses inside the laser cavity simultaneously, then you can get a high repetition rate, which is called the harmonic mode locking technique. But when you do that, there is a price. When you do the harmonic mode locking, then it creates another type of noise which didn't exist earlier, which is called the supermode noise I said a little bit earlier. And when you look at here, there's several spikes, and these are the supermode contribution. So when you add this and this together, it seems like we don't really gain much by doing this. But there's a technique to get rid of it, which is by inserting the Fabry-Ferro-Etalon inside the laser cavity. So conceptually it's doable, but practically it's very hard to build it. First of all, we have to match this the Fabry-Ferro-Etalon with a laser cavity, and if there's any external disturbance, then the laser cavity and Fabry-Ferro-Etalon can be very easily out of tune. So it required very sophisticated feedback control. But anyway, we did it. This is a laser cavity, and then there's a gain medium, and then there's an Etalon. And then for this, we need a very sophisticated feedback control. This part is called the pound river hole feedback loop, and then this is a phase lock loop. And then with all that working together, then we get this kind of result. Here we have a little bit of remain of the supermode noise, but I call it success. So we bring the D frequency low using this technique, and then we can actually eliminate the supermode noise and then making the laser quiet. There are a million different methods to lower the noise, and then also the science of noise itself. But I'm just trying to give you an idea. And then this is the actual box that we built.
Dr. Gee.
Yes.
So this is exciting. Can you describe for the students, number one, this was published in a paper, but this would be patented as well, or?
This, I don't think we patented this.
Okay.
Yeah.
And where were you working at the time, 2005?
This was done in the Florida.
In Florida.
Orlando, Florida.
So you're working for the university
Yeah.
and came up with this technique. Okay,
Yeah.
thank you.
This was a part of the DARPA project. And once you have a very low noise laser, actually you can do something else. Let me, yeah, this timing. So next example is the signal processing, optical signal processing. We can use this laser technique in the analog digital conversion. When you talk about the analog digital converter, there are two parameters that really determine the performance or quality of this analog digital converter. One is the sampling rate, the other one is the resolution. Resolution is usually given as a number of bits that is possible. So this is a chart. Usually in the music business, they use the analog digital converter that is located in this area. Many other commercial analog digital converters are in this range. And then this is the range that defense industry is interested in. There's a trade-off between these two qualities. As you go to the higher and higher sampling rate, your resolution drops. And operating this is very, very hard. But in the military, they're dying to have an analog digital converter in this range. The reason is something like this. When something, the enemy missile or anything comes in, it can be detected by the radar. The radar output signal is the analog signal. And this has to be digitized. And then once we change the digital signal, and the supercomputer can calculate and then tells this is a dummy warhead or it's a real warhead, and they can do all kind of calculation. But this has to happen very quick. So they need a very, very high-speed analog digital converter, and defense has been dying to have that kind of analog digital converter. When we use the optics, then this is the schematic of the typical analog digital converter. It has 4 steps, and then when we use the optics, the second step is the step that we contribute the most. First step is the filter. There's nothing we can do about it. And the second part, the sampling part. And once the signal is properly sampled, then the actual quantization is done by the conventional electronics, and then it can be coded. So only this portion is what the optics is intervene. And this is one of idea. It starts with a mode lock laser with a relatively broad optical bandwidth, and then it goes through the dispersive element. When the pulse goes through the dispersive element, the dispersive means different color or different wavelengths of the pulse experience different index of refraction or different optical path lengths. So in other words, if the laser pulse has a broad spectrum, one part it has a red, blue, green, then red has has a much longer optical path length than blue. So when this pulse goes through the dispersive element, at the output end, the different color are all separated in time. So if I plot it, we can get something like this. This horizontal axis is time, and then the vertical axis is the instantaneous frequency of the pulse, and then you can have a linear relationship. So that means the front part has a low frequency, and then the tailing edge of the pulse has a high frequency. And depending on the sign of the dispersion, we can actually have opposite too. So this is the kind of cartoon. Let's say we have a pulse, and it was originally color, but when I copied it, it became black and white, but it's a little hard to see it. But let's say this different brightness corresponds to different color. And then this pulse goes through the modulator. And then let's say we have an electrical signal. This is a signal from the radar. And this is very fast signal. And this is a signal that we want to change into digital signal. And this signal feed into the modulator. Modulator is using the electro-optic property, and which is really, really fast response. It's almost instantaneous. So this modulator can respond to this fast signal. There's no problem. When this dispersed pulse goes into the modulator, then this signal is encoded into this pulse in terms of the intensity. So you can see that the intensity profile is exactly matched with the electrical signal. Once that the signal is encoded in terms of intensity of this pulse, this chirped pulse, we send this to the second dispersive element. And then this pulse experiences more dispersion, and then it stretched even farther. So we get something like this. Now, let's compare this guy and this guy. It has the same shape, but when you look at this has been stretched in time. So this is as if looking at this signal in the slow motion in the movie. So it moves much slower. So after that, we detect this signal using the conventional photodetector and then using the conventional analog digital converter. Then we can actually, yes.
So Dr. Gee, this is interesting to me. You're saying the military applications was this high frequency. So I sort of assumed that they needed the signal really quickly.
Mm-hmm.
This doesn't get you the signal quicker, but it allows you to sample, it stretches it out so you can sample it more finely or at higher frequencies. So they're looking for changes in signals. When the military are looking for it, they're looking for changes in the signal that happen very rapidly.
Yes, yes.
Okay.
So yeah, maybe I wasn't really clear what the quick sampling is. So let's say this is the signal, then the high frequency sampling means that we want to sample as many points in this data as possible. And then in the conventional electronics, because electronics is slow, we can sample maybe 2 points in this data, then it's meaningless. But by doing this, after we stretch it, we are using the same analog digital converter, but we can sample more points in the same data. So in effect, it has the same function as the sampling at the high rate. So that is the one technique that people did. And then this is that there are many different architecture. I'm just giving you a couple of ideas. And the encoding part is the same. We have the chirped pulse that has amplitude as the signal encoded. And then instead of sending this to another dispersive element, we send this pulse into the optical device that divide a different spectral segment and then send it to different channel. And then at the end of each channel, there's again conventional analog digital converter, and then we get the digital signal. And then after we get the digital signal from these 4 different channels, we combine them together to have a composite image of it. Then it also does this similar work. So the reason that I worked in this project is because conceptually it's very simple, but when we try to realize it, then there are a lot of technical difficulties. One is that making this model lock laser very, very quiet. It requires very, very low noise laser. So that's how I got involved with this project. Let me move on to the next topic. This is an example of the nonlinear optics. The Dutch physicist Christian Huygens noticed about 300 years ago. He was also a clockmaker. He had a grand power clock, and at the beginning, that the clock was the pendulum was oscillating randomly. But if you just leave it for a long time, then they move in unison. Always it happened. So he was curious why that happened, and now we know it so well. We call it injection locking between 2 oscillators. So let's say we have 2 pendulums, and we all know that the frequency of the pendulum is defined in this way. Only the length of the pendulum defines the frequency, not the mass. This is the general physics question. So let's assume that the pendulum length is very similar, not necessarily equal, but similar enough. Then the energy of the one pendulum can be injected into the other pendulum by sound or vibration through the wall or whatever. That can be very, very minute, but still they can exchange energy. By exchanging the energy, they become synchronized. And then this is a well-known phenomena. And then we can expect something similar in the laser. Let's say we have a one laser cavity and then other laser cavity, and then the frequency was kind of similar. Then we tap up the little bit of the output of the one laser and then send it to the other laser. Then before long, they are all synchronized. They operate at the exact same frequency and same phase. One is the master, the other becomes slave. So, and then this, again, is well-known phenomena. But let's make it a little bit more interesting. Now, the master laser is a CW laser. It has only one mode in it. But the slave laser, we take the mode lock laser. And then in the mode lock laser, there are many, many modes excited at the same time. So if we inject the mode of the CW laser into the mode lock laser, what will happen? The one scenario that we can easily imagine is something like this. Let's imagine in this case there are only 3 modes in the mode lock laser, and also let's assume one of the pendulum has a similar length as the CW laser pendulum. Then we can imagine, okay, if the energy goes in and then this guy, since this guy and then this guy is similar, there can be an injection locking. So this guy and this guy is synchronized. And then also by the mode locking mechanism that I had said earlier, there could be some sort of phase locking mechanism between this pendulum and this pendulum and this pendulum and this pendulum, which was symbolized by this blue springs. So at the end, maybe all these 3 pendulum is synchronized with this guy. That's one thing that we can imagine, and then that's actually the case. This is the experimental setup. We have a single mode laser, and then it goes into the mode lock laser, and then it's detected, and then there is a diagnostics. And then when we do that, this is the result. This cartoon explains what's going on. Single mode laser, and then this is a many mode from the mode lock laser, and the single mode is overlapped with one of the mode in the mode lock laser, and then it locks. This is the optical spectrum. There are 3 plots in this graph. This gray dotted line is the original spectrum of the mode lock laser before locking. So we have several modes, and then they're separated by 10 gigahertz. And then there is a dotted line. This is the CW laser spectrum, this one. And then the solid line is after it has been injection locked. You get something like this. But this is the optical spectrum analyzer output, so you can't really tell whether there is a locking is done or not. The resolution is so poor. So really see it, we need to rely on better technique called the heterodyning. We send this output into the photodetector, and then photodetector signal goes into the electric spectrum analyzer, and then we can measure the beat signal. And then this is the RF spectrum analyzer output when it wasn't really locked. What we see here is that there is one very well-defined 10 gigahertz tone. That is the beating between this mode lock, the individual mode in the mode lock laser. And there's 2 side bands, and then they're broad. What happened is like this. If these are the mode from the mode lock laser, and the CW laser is here, when they are not locked, they're kind of dithering like this. And the beating term also will reflect this dithering effect. So when you measure the beating frequency of the beat term, they will have some width, and that's what is happening here. Instead of one sharp, nicely defined peak, we have a broad beating term. Once that is locked, they disappear, and then just we have one single line. So this is a real evidence it locks. So okay, that's fine, but let's make it more exciting. Let's inject this light into the mode lock laser where there's nothing similar as Egypt. And then if you expect there will be injection locking, but then you're trying to inject injection lock to the ghost, because there's nothing on it. But if the certain conditions are satisfied, we can still achieve the locking. For example, if the frequency of the CW laser is exactly in between these two, locking can be happening. And that's the example. Oh, wait a second. This is before it is locking. And now we have one more B term. And then once the locking is done, these two side mode collapse into the delta function-like tone. The reason that we have a 5 gigahertz tone is because, as you can see here, this pulse is, this mode is 5 gigahertz away from the neighboring one. So on top of this 10 gigahertz one, we'll have a 5 gigahertz, 5 and 15 gigahertz one. Not only that, we found out, actually, it doesn't have to be only in the middle. If you have a 2 mode separated, and then if you divide it by integer, then any of those points you can lock to. So in this case, the next example, we divide it by 3. And then we lock it, then this is evidence it is still locked. So this is a very interesting example, and we did the modeling, and it perfectly matched with the simulation. What happened is that when they are close but not locked, then by the four-wave mixing, it creates a lot of side mode, and then this tiny peaks actually pulls each other. They want to do the injection locking to each other, the smaller one. So they bring these tiny side peaks, and then when they are close enough, they just collapse into just one. And then as a result, we achieve the injection locking. We have only a few minutes left. Let me just go over this last topic. This is how we can use the laser in the micromachining. Let me first talk about the athermal ablation. When the light intensity is so high, then as soon as the light hit the material, it just ionizes the whole material, even before it heat up. It doesn't have a time to heat up. So it just the material just ionized and then just become a plasma. This is a typical numbers, pulse width and the pulse energy. And if you focus this laser output into this tiny spot using a lens, we can achieve this 3 micrometer of the spot size and then about 20 micrometer of wavelength range. You can calculate the energy density at the spot, which can be given like a 600 kilojoule per cubic centimeter. Let's compare this energy density with the diamond. Diamond is considered as the hardest material in the world, and it's made of the carbon atoms, and then they have a double covalence bonding. And then we know the bonding energy, so I can calculate how much of the bonding energy density there is, which is about 250 kilojoule per cubic centimeter. If you compare this and that, this is way higher. So in front of this intense laser light, it doesn't really matter whether that is a diamond, a sapphire, or titanium. Everything just evaporates instantaneously without causing any heat. And then that's important in the industry because it doesn't deposit any heat. It doesn't cause any thermal damage in the neighboring area. So one of the applications is the direct gas injection. This is the conventional gas injection. This is a direct gas injection. The injector injects the fuel into the cylinder directly, and then this is the blow up of the nozzle, and it has a holes about 100 micrometer in diameter. And by making this holes right, you can improve the gas mileage about 15%. Just drilling this hole right. Why? When the hole is correctly made, then you can actually spray the gas more efficiently or in a more desired way inside the cylinder, and then that improve the gas mileage. So that's why the industry is interested in. And this is the nozzle made by the conventional method. It's called the electric discharge method. And then you can see the roughness in the surface. This is when the nozzle was cut by the femtosecond laser. So it clearly tells you the difference. And then it has also application in the cardiovascular stent fabrication and or in the consumer electronics, cutting the cell phone glass. So people are interested in using laser to cut materials. And when we do that, we want to optimize the laser. So we want to optimize in all three different dimensions, both temporal and spectral and spatial dimension. And the spatial dimension, we do the beam shaping. And for example, if the beam has some sort of aberration, then using some sort of the beam shaping technique, we want to make the aberration-free beam, and then we focus it, and we can get a very tight focus. And we also learned that for the glass cutting or transparent material, we learned that instead of sending one intense pulse, if you have a burst of several pulses, it cuts much better. And then for that, we again need to optimize it, what the perfect distance between pulses are, and then the relative intensity between pulses, things like that. So using the technique called the pulse shaping, we want to optimize the pulse for the given application. And the spatial beam shaping, we use the technique called adaptive optics. Dr. Severson is the expert of this area. Using this deformable mirror, we can really compensate if there's any distortion of the wavefront, and then create a very crisp image at the end. But not only it's used to compensate the aberration in the beam, in our case, actually we start from the laser beam and then send into the deformable mirror, and then we tap up a little bit, send it to the wavefront sensor, and then most of the beam goes through the telescope and then scanner, and then it cuts in this portion. So this is the image of the deformable mirror, and this is the far field pattern when we do the this kind of image processing. I mean the beam shaping. Let me just give you this example. So I said earlier, for the transparent material, sending two pulses is better than just sending one intense pulse. It has to do with the mechanism. The fact that material is transparent means that the band gap of the material is much larger than the energy of the incoming light. So it does not absorb, it just becomes transparent. But if the light intensity is very high, then it can still be absorbed by the process called the multiphoton absorption. But this has a very, very low efficiency, and it hardly absorbs. But if the light is intense enough, then you can still ablate the material using this multiphoton absorption process. But instead of doing this, if you send just the decently intense pulse, so it doesn't really ablate the material, but it still can have some amount of the multiphoton absorption. You can bring the electron from the valence band to the conduction band, or any impurity level. And then these have a certain amount of decay time. And then if you send the second pulse before they decay, then there will be absorption caused by this guy. These absorptions are linear absorption by free carrier absorption. So this absorption is really, really efficient. So, and this absorption will cause the avalanche ionization process, and then you will directly connect it to the athermal ablation process. So, because of this mechanism, we try to optimize the pulse train, and then this was just a brief discussion how we do the pulse shaping. And but let me stop here. So this is a summary. This is what I did. I talk about the how to make the femtosecond laser, and then and how to measure, and then these are the applications that I mentioned. I'm sorry that it took so long.